All right, John pours salt water solution that contains 40 grams of salt per litre into an empty container at a rate of 3 litres per minute. How much salt is entering the container each minute? So in this question, I'm asking for the rate at which the salt is going into this container each minute. It's an amount of salt, but how much of it is going in per minute. And once I know that, I could actually find an equation just for the amount of salt over time. But the question is just wanting at the moment to clarify what is the amount of salt per minute. Now, I find it easy to write things down with units here. So I can see that we're pouring in solution with 40 grams of salt per litre at 3 litres per minute. So we're going to get 3 litres per minute of these 40 grams per litre. 3 litres per minute of these 40 grams per litre. So I'm just multiplying together the two rates. We don't often do this, but I find it helpful to multiply and treat the units kind of like algebra to find out what the final answer is. So this is actually 3 times 40 is 120. And the litres cancel, and I get grams on the top and minutes on the bottom. So it's grams per minute. So that answers the question, how much salt is entering the container each minute? 120 grams per minute. Now, because that's constant, you could say, well, I want to know how much salt is there after 10 minutes. You could just times that by T. But it's actually a differential equation. And the rate at which the amount of salt is changing is positive because it's increasing. And we would say that if Q is the quantity of salt, the rate at which this quantity of salt is changing is positive, and it's 120. And that's very simple to find the equation for Q to solve that differential equation because it's just got a constant. So I could just integrate both sides with respect to T straight on up, and I would get Q is equal to 120T. Now, of course, there's the constant of integration, but looking at this, it was an empty container, so it would be 0 at the start, and I would end up getting C is 0. Therefore, that's my answer for the amount of actual salt in the system at any time. Of course, the question was just wanting to know the step before that, how much salt is entering the container each minute. So I want to know, for this situation, what the amount of salt is at any particular time. And the first thing I need to do is to look at how much salt is there at the start, how much is going into the system, how much is coming out of the system, and put all that together to figure out how much salt is there at any particular time. Now, the best thing to do is to look at the rate of change of the amount of salt over time, form that equation, and then, like I did previously, solve the differential equation to get the amount of salt is equal to some function of time. So I'm just going to pause this because I need to clear a couple of desks out of the way so I can slide my computer along to be able to film this. So one moment. All right, now I'm able to move backwards and forwards here. We can concentrate on this question and actually move across, get some room to work. Now, very important, what's in the box here? The rate of change of the amount of something, like salt, over time is equal to the rate at which salt comes in minus the rate at which salt goes out. And in our previous question, we only had salt going in. So we had a positive rate of change. But if more salt went out, well, then overall we might have a negative rate of change. So let's have a look what's happening here. A tank contains 10,000 litres of brine, which is just salt water, with a salt concentration of 1 kilogram per 100 litres. And then brine with 2 kilograms per 100 litres enters the tank at a rate of 20 litres per second. The well-stirred mixture leaves at the same rate. Now, I haven't written a question, but what I'm wanting to do is get an equation that tells me the amount of salt that's in this tank at any particular time. So first of all, I need to find out what dq dt is, like the rate of changes that are happening are going to then allow me to get a rate of change equation, which is a differential equation, and then I'll solve that rate of change equation to find what the quantity of salt is at any particular time. So I'm going to look at the rate of salt entering minus the rate of salt leaving. Okay, so all we've got here is we've got a container, and the container has 10,000 litres of salt, and the salt in there is at 1 kilogram per 100 litres. And we're pouring in salt water. So salt is coming in because we care about the amount of salt. And this salt is 2 kilograms per 100 litres. And we're also pouring out some solution, and the solution that's leaving here is leaving at 20 litres per second. And the solution that's going in here this way is going in at 20 litres per second. So there's our information. And we're going to do what this box says. We're just going to say that, well, the change in the amount of salt totally in that tank over time is going to be equal to the amount of salt entering, the rate at which it's entering, minus the rate at which it's leaving. So I just need a little bit of room here, which is why I've cleared those desks so I can move along. Let's use this for working. dq dt equals. Now, I need the rate at which the salt is entering, first of all. Well, it's going in, we've got 20 litres per second of something going in. Of what? Of a 2 kilogram per 100 litre solution. Now, I've written my units a bit strangely, but that's because I'm going to actually cancel things out and come up with a final unit, treating them kind of like algebra. That's the salt that's entering, the rate at which salt is entering. Now I've got to minus off the rate at which it's leaving. Now, I get 20 litres per second leaving of, and now that's a bit tricky because I need to know the concentration that's in there. Well, I don't know how much salt is in there. It keeps changing every moment because some of this highly salty water is going into less salty water, and then you're removing this mixed up solution. So the amount of salt in there just keeps changing all the time. So it's been called Q. We're saying the rate at which the amount of salt is changing over time. The amount of salt is clearly Q, the amount of salt in there. So I've got some amount of salt in this system, and that amount of salt that's in there is in this 10,000 litres. So if the concentration will be that amount of salt, that many kilograms of salt in 10,000 litres of solution. Now we're lucky because 20 litres is coming in, 20 litres is going out, so that volume 10,000 stays the same. But I'll do a question in a minute where I change up the volume as well, and we're going to have to alter what we put on the bottom of here because we've got to figure out what the overall volume is. So I've got the rate at which salt is entering the system over time, the rate at which it's leaving the system over time, and now I can sort out what my dQdt equals, the total rate of change of salt in the system there. So that litres is gone, that litres is gone, and we've got 20 times 2, which is 40 on 100, so 0.4. I've got 0.4, and kilograms is on top, and seconds is on the bottom. So 0.4 kilograms per second is entering, and then leaving. This says 20 Q on 10,000. 20 Q on 10,000. So that's 2 Q on 1,000. That's 1 Q on 500. Right? It's Q on 500. And then once again, we'll have litres are cancelling, and we've got kilograms per second. So altogether, the rate of change is 0.4 minus Q on 500 kilograms per second. Now, kilograms per second is not such a big deal to me anymore, but I will just keep it there. But if you didn't put that there in an exam, I'm sure they'd be happy with dQdt equals 0.4 minus Q on 500. Now we need to solve that differential equation. dQdt equals 0.4 minus Q on 500. So I need to push my table across so I can get a bit more room and have a chance to solve that differential equation there. So let's just move these couple of things off the board and we continue on. So we had dQ dt equal to 0.4 minus Q on 500. And that's what we've been asked to solve. So what I'm going to do is I'm going to actually factorize that out and get that 1 on 500 out the front. So this is the 1 on 500 come out the front, something minus Q, because that's going to be more simple to work with. So just one moment, 200. So that'll give me my 0.4. Now I'm going to separate variables. Uh, 1 on 500 dt, and I'm going to integrate. So this one will be negative the natural log of 200 minus Q, and this will be T on 500 plus C. Now, at the beginning, we had ourselves a tank with 10,000 litres in it at a concentration of 1 kilogram per 100 litres. So I need to know what Q is at the start. 10,000 litres, how many hundreds goes into that? 100. So we had 100 kilograms of salt in there at the start. All right. So when T is 0, this was 100. So that means 200 minus 100, that's 100. So C is equal to minus the natural log of 100. So that means now I have that minus the natural log of 200 minus Q equals T on 500 and minus the natural log of 100, because that's my plus C. And I just now need to do that act of getting the Q as the subject. So I've got natural log of 200 minus Q and minus the natural log of 100. So I don't know why I decide to change the signs midway. How about we just stick with the signs as they would be? Natural log of 100 minus natural log of 200 minus Q equals T on 500. So that's natural log of 100 on 200 minus Q equals T on 500. So 100 on 200 minus Q is equal to E to the T on 500. So 100 equals 200 minus Q, E to the T on 500. And we need to get that. So 100 equals 200 E to the T on 500 minus Q E to the T on 500. So Q E to the T on 500 equals 200 E to the T on 500 minus 100. So Q, yes, you can see that, Q equals, and I divide by E to the T on 500, and I'll get 200 minus 100 E to the negative T on 500. And you can sort of check whether that's on the right track by saying, well, when time is 0, then there should have been 100 kegs of salt in there. So you put time is 0 and you get 100, 200 minus 100. And so that's the quantity of salt in there over time. Now I'm going to do another question, but I think this video is getting too long, so I'll roll it into a different one, where we have the same system, but how about we change the rate? Like maybe still put in 20 litres per second of that 2 kilogram per 100 litre solution, but let's only remove, say, 10 litres per second and see what difference that makes to the setup here.